You know about classes, but you may be thinking, which traffic goes into each class? And how many classes should I configure? Well, let me help you simplify this. You don't need to use every combination of class and drop probability. You might keep it simple with a 4 or 5 class model like the one shown here. In fact, this is a very good place to start. There is a real-time class for voice and interactive video. This is a high priority class. Next, a class for critical data. This is for your business applications, databases, website traffic. We could split this into 2 classes. The point would be to give call signaling traffic like SIP a higher priority. Now, if you're not familiar with SIP, it's the traffic that sets up phone and video calls. The next category is the best effort category. This would be the default category, so any packets that didn't get marked would end up here. This is the class default that we configured in the last video. And finally, the scavenger class. This is traffic that is even less important than the default traffic. Now, this might include something like online games, for example. Things that don't usually have any business relevance. Often, we limit traffic in this class to a very small amount of bandwidth. So what markings might we apply to these categories? There are only 5 categories here, so once again, that's really simple. Real-time traffic gets marked with expedited forwarding. This indicates that it needs quick and uninterrupted handling. Call signaling is also pretty important, as it sets up phone calls in the first place, so it would get a marking of either AF31 or CS3. Either of those would be fine. Our other critical data would be a little lower than this, so we might use something like CS2. Best effort traffic would have the BE marking. This means setting the DSCP bits to all 0. That's why this is the default class. All 0 bits means unmarked traffic. The scavenger class is lower again with the CS1 marking. Remember that these are all examples, and you could use different markings if you want to. But this makes it easier to add more classes later. More complex networks with more applications may need more complex class models. Cisco has a few recommended models on its website. I'll put a link in the description if you're interested in seeing them. Applying actions to a queue often involves a process called queuing. This is true for actions such as reserving bandwidth. Each physical interface will have several queues, usually 8. We're showing 4 here just to keep it simple. When a router is ready to send a packet out, it will add it to one of these queues based on its class. When the interface is ready to send, the packet moves from the queue and the router sends it out the interface. There will be many packets that a switch or router has to deal with, but a single interface can only put one packet on the wire at a time. So what happens when there are many packets spread among different queues? How does the router decide which packet to send next? A component called the scheduler handles this. The scheduler looks at the priority of each queue and will decide which queue to service next. And that gets to the heart of how QoS prioritizes traffic. The scheduler services a high priority queue more often than a low priority queue. One very simple option is to use round-robin scheduling. This method cycles through each queue, servicing each one in order. That is, it will take some packets from Q1, then Q2, and so on. After the last queue, it begins again back at Q1. The downside is that this gives all the queues the same amount of attention. We don't really want that. We want the high priority queues to have more attention than the low priority queues. Weighted round robin is a refined version of this method. The scheduler still services these queues in order, but it spends more time on higher priority queues and less on low priority queues. Each queue gets attention, but higher priority queues get more attention. On a Cisco router, there is the class-based weighted fair queuing scheduler. This uses the weighted round-robin algorithm. In effect, this algorithm provides a guaranteed amount of bandwidth to each queue. But this is only when there's congestion. When there's no congestion, classes are free to use more than their allocation. Another option is strict priority queuing. In this method, one queue is the priority queue. It is completely serviced before even looking at the next queue. The point of this is to give maximum attention to the highest priority of traffic. To find some balance, you could use low latency queuing. This is a hybrid between class-based weighted fair queuing and strict priority. One queue is the priority queue. This is where you put your real-time traffic. The CBWFQ scheduler services the remaining queues as normal. So the priority queue bypasses the CBWFQ scheduler and is always served first. There are pros and cons to each method, of course. The method you use will depend on the environment and the type of traffic that you have. Class-based weighted fair queuing is good for general traffic, but hurts real-time traffic. That's because packets in the real-time class can queue up while the router services other queues. This delays them and adds jitter. Strict priority queuing is great for real-time traffic, but it's bad for everything else. If there's a lot going on in the real-time queue, the rest of the queues don't get serviced as often. This can lead to queue starvation. This neglects some lower priority traffic, even though it's still somewhat important. An advanced solution to this is to have a priority queue, but put a rate limit on it. We'll see how to configure rate limiting very soon. But first, let's look at configuring the 4-class model. We'll start by configuring the 4 queues that we've been looking at in these examples. This time, we're going to match based on the existing DSCP markings. Let's continue by configuring the priority queue. We do this under a policy map as normal. Within the queue, we use the priority statement. This is very much like the bandwidth statement we saw in the last video. The priority statement allocates bandwidth, but it also identifies this queue as the priority queue. Now we can create the rest of the queues in regular class-based weighted fair queuing mode. In the last video, we used a percentage of bandwidth. We could also use a fixed value. For example, I could set 1 megabit on Q2. We could allocate a percentage of the remaining bandwidth if we want to. But as we see here, we can't do that when we've already set a fixed value on another queue. So we'll allocate, 500 kilobits here. We don't need to explicitly configure Q4. We can leave it to just get whatever bandwidth remains. As normal, the final step is to apply this policy to an interface with a service policy. As this policy involves allocating bandwidth, we'll apply that in the out direction. What happens if a queue fills up? Packets need to drop. By default, the router drops the newest packet. This is called a tail drop, as the packet drops from the tail of the queue. Of course, this could be a very important packet. Dropping it only because it's the last packet to arrive is not ideal. This is where the drop priority can help. Remember, this is a bit like a subclass within a class. The drop probability can be low, medium, or high. When a queue fills, the router drops packets marked with the high drop probability first. This makes room for new packets to enter the queue. If there are no packets with a high drop probability, the router drops medium packets. Queuing means that a router can spend more time servicing important traffic. Drop probability lets us be more granular. It allows us to set priorities within a queue. Two tools often used with QoS are policing and shaping. They're very similar as they are both used to rate limit traffic, but there are still some subtle differences. This is where we define a limit based on how much bandwidth certain traffic can have. This could be a type of traffic, like FTP downloads. Or it could be traffic between two IP addresses, or some other combination of conditions. First, think about the traffic we've identified. As shown here, it's common for traffic to increase and decrease over time. The high peaks in the graph show this. When we configure policing, we're setting a hard limit. That is, a limit to the amount of bandwidth that this traffic can have, as shown by this line. Any amount of traffic under this is called conforming. Anything above this limit is non-conforming. The whole point of the policer is to take action on any non-conforming packets. The simplest and most common action is to drop all non-conforming packets. This strictly enforces the rate limit. It would change our traffic pattern to look more like this. Another option is to remark non-conforming packets rather than dropping them. We could raise the drop probability or move them into a different class. This might be useful if we'd rather an upstream device decide which packets to drop. A policer is able to recognize a small but short burst in traffic that goes over the limit. In a case like this, the policer will still consider this burst to be conforming. It will not take any additional action. However, a large increase of traffic or traffic over the limit for an extended duration is not a burst. This is non-conforming. The point of this is that a policer is a little bit friendly. It won't penalise your traffic for small infractions. We'll now try to configure a policer. Before we start, let's check the service policy on this router. Here we have Q1 configured as the priority queue. Let's rate limit traffic in this queue to 100 meg. To start, we edit the policy map and then the Q1 class. This is where we'll define an extra action. We'll use the police action. This is the policer or rate limiter. I often type confirm instead of conform. I'll fix that up. Okay, that's better. Let me explain what this command is doing. Police is the action, the rate limiter. I've set it to a limit of 100,000 kilobits per second, or 100 meg. We then need to set two different actions. What happens to conforming traffic and what happens to non-conforming traffic? I've chosen some basic actions: allow or transmit conforming traffic and drop non-conforming traffic. Now, if we look at the policy map again, we can see that the priority command is still there. We haven't affected that, but we have now added a policer. Now, there is a warning that comes with policing. Some traffic types don't respond well to drops. Reclassifying can also be tricky, as packets may be out of order, which is bad for some types of traffic. The point here is that it's important to understand the effect of policing your traffic before you apply it. Shaping is a rate limiter like policing, but in a way it's a little bit gentler. It still looks at non-conforming traffic, but instead of dropping or remarking, it adds non-conforming packets to a queue or buffer. When more bandwidth becomes available, the router sends out these buffered packets. This works well when dealing with small bursts in traffic. Instead of cutting these peaks off, we're smoothing them out. We're changing the shape of this graph. We're smoothing out bursty traffic. Let's go back to our router and add shaping to the Q2 queue. This is an extra action under the policy map and under the class. We can now use the shape average command. Here I've used 10,000 kilobits per second or 10 meg. Nice and easy. Now, this comes with warnings too. If your traffic bursts are too large, the queue will fill up. The queue will not accept any new packets when it's full, and when this happens, tail drops will occur. Also, not all traffic likes shaping. Shaping delays packets. This is generally not a good thing for real-time traffic. Real-time traffic needs consistent and regular delivery of packets. We've nearly finished our discussion on quality of service. Before we move on to IPv6, we have just one more thing to say about congestion. It's likely that you've noticed that a large part of QoS is managing congestion, especially how to manage traffic when congestion occurs. Another aspect of QoS is avoiding congestion as much as possible. We can't prevent it entirely, but there are a few things we can do to help reduce it. To understand that, we need to think about how TCP works, in particular, acknowledgements and windowing. When traffic uses TCP, the receiver will send back an acknowledgement. This confirms that the packet has arrived. If a sender does not get an acknowledgement back, it assumes that the data has been lost and will resend it. Now, it's not effective to send an acknowledgement for every single packet, so TCP uses windowing. The sender and the receiver agree on a window size. This is the amount of data that a device sends before it needs to be acknowledged. The receiver then sends a single acknowledgement for all of this data. The sender will pause and will wait for the acknowledgement before sending more data. If the acknowledgement is not received, all data in that window needs to be resent. Usually the window size starts small. Receiving acknowledgements increases confidence that the link is stable, and both parties will start growing the window size. If acknowledgements go missing and data needs to be resent, then the window size will start to shrink. This is to reduce the amount of data that needs to be resent over an unreliable link. The key point is that smaller window sizes mean more acknowledgements. This means the sender spends more time waiting and less time sending. Now, back to queuing. Queues have to limit how many packets they can store. This is the queue limit. The number of packets in the queue is called the queue depth. So, before the queue fills up, QoS can drop a few random packets. Now that sounds weird, but there's actually a good reason for this. A few drop packets before the queue fills tricks the receiver. It thinks that there is data loss. This means that they won't send an acknowledgement for that window of data. This means that the window size will shrink. The smaller window size means the recipient will send acknowledgements more often. In turn, this means that the sender will slow down as it needs to wait for acknowledgements more often. The result is the sender will not send traffic as quickly, which means less congestion. That's not to say that the router will start dropping packets at any time. There's a threshold for when it's an acceptable time to drop traffic. And of course, we can drop less important traffic first. It's all based on the queue depth and how full it is. First, there's a configurable minimum threshold. If the number of packets in the queue stays at or below this point, there are no drops at all. This is a completely healthy link. The next level is the maximum threshold. When the queue depth is between the minimum and maximum, the router drops a small number of packets. When the queue depth is over the maximum threshold, QoS triggers a full drop. If you're interested in knowing more about how this works, I recommend having a look at my QoS mini-series. The process we've just described is random early detection, or RED. There's a more refined version called weighted random early detection, or WRED. You might see a bit of this in the lab. Now, in this lab, you need to configure the 8-class QoS model. First, you need to fill out the table shown here with the requirements. This includes the DSCP marking to match, the bandwidth, and any extra requirements. You'll find some links in the description that will help you to find this information. Once that's done, you need to configure this on the two routers as shown here. That brings us to the end of this section. Things are sure to be interesting in the next section as we begin looking at IPv6. This is the newer version of IP, which comes with an all-new address format. I really hope to see you there.